So 2.4 is where we're at. We're going to go kind of quickly through this section because I know that you'll spend a great deal of time in Algebra 2 going over this topic. We're going to introduce, though, a few more functions that I want you to be responsible for. So 2.4 is parent functions and transformations. What is a parent function? A base function, a function that is a parent. Is it a single parent or is it in a loving relationship with another function? I think they're single parents, right? So would they be the father or the mother? Mother would be a good analogy because a lot of these parent functions have offspring, right? Other functions that are generated from them. So I guess mothers can give birth, right? So you can call these parent functions or you can call them mother functions. You just got to be careful how you say that, okay? And what we're going to do with these mother functions is learn what the basic function looks like. Then from that, by just manipulating the equation in a certain way, we're going to manipulate the graph in a very predictable manner. So what are the functions that you need to memorize? This is your catalog of parent functions, okay? Of course, we got f of x equals x. That's your linear function. That's the one you studied in Algebra 1, right? Algebra 1, you studied x to the first. Then in Algebra 2, you added a 2 to the exponent, and you got x squared, right? That's why they call it Algebra 2. And you studied these quadratics. So those are the two most basic ones. Algebra 3, has anyone taken Algebra 3? You study cubics in Algebra 3? You maybe have gotten to these in Algebra 2 as well. These are your cubic functions. And those three right there belong to a larger family of functions called what anomials? Polynomials, cool. And we're going to study those very briefly here in the next couple of sections. So those are your three polynomial parent functions. There are other polynomial parent functions, x to the fourth, x to the fifth, so on and so forth. But these three are the big ones. Then we have your radical function, the square root of x. This is going to be half of this quadratic that opens up, and we're not going to look at this piece down there because it wouldn't be a function. So you have the radical function that only lives to the right of 0 and at 0. And then we have, this is a new function maybe that you haven't seen. So here's the first new one of the day. F of x equals e to the x. Now, first of all, what is e? You would think it's any number because e is a letter, and a letter could be a variable, and a variable could be any number, right? Yes, it's actually called the natural base, or the natural, we'll call it the natural base here. It's like pi. Pi is a transcendental irrational number. It's a non-terminating, non-repeating decimal. E, in mathematics, is much like pi. It's a transcendental irrational number. It's about 2.718 ... So it's a little bit less than pi. Sometimes it's called Euler's number, Euler with an E. Sometimes it's called the banker's number. But right now we're going to call it the natural base. Now, whenever you have a number raised to a variable power, you don't have a polynomial. Okay? What type of function is this where you have a numeric base but a variable exponent? This is an exponential. Okay? So this is going to be our parent exponential function. And you maybe have seen these before, but maybe you looked at 2 to the x, right? Cell division, mitosis, meiosis, that follows an exponential function 2 to the x, because every cycle of x, when x equals 1, 2, 3, 4, the population doubles, right? The cells divide. 1 becomes 2, 2 becomes 4, 4 becomes 8, 8 becomes 16. That's exponential growth, okay? And exponential growth will grow a lot faster than polynomial growth for large values of x. So this is 2.71 to the 8, 2.718, sorry, to the x. It's the exponential function. And what do we notice about it? Let's talk about some things. The domain of this function is what? What do you think? Looking at the graph. Negative infinity to positive infinity, so all real numbers. Okay? You can raise e to any power. What's the range? 0 to infinity. Do we include 0? No, because if you raise any number like 2 to any power of x, or e to any power of x, it's never going to equal 0. Okay? But if you plug in a big enough negative number, it'll get smaller and smaller, approaching 0. So this range is from 0 non-inclusive up to infinity. Now, here's what's important about it also, the end behavior. What would be the limit as x goes to infinity of this function? Infinity, right? And it goes to infinity pretty darn quickly. Exponential functions that are growing go to infinity pretty quickly. But what is the opposite end behavior? If you went to negative infinity, it goes to 0. And remember, we've defined this now. Anytime you have an end behavior limit equaling a finite y value, what graphical feature do we know lives there? Horizontal asymptote. So this graph has a ha at y equals 0. So you could draw it in there like that. But notice it only affects the graph on the left side. So even though you can draw it all the way across from east to west, or I guess you can draw it from west to east, it only affects the graph way out west. Yeah? Any symmetry to this graph? X-axis, y-axis, origin? No, no symmetry. There is an interesting point right there. What is the y-intercept? 1, right? You can find a y-intercept by plugging in a 0 for x, and of course e to the 0 is the same as 2 to the 0, which is the same as 5 to the 0, which is 1. So it passes through the point 0, 1. Is it monotonic? E to the x always passes through the point 0, 1. Yep. Right, because what's e to the 0? 1. 1, yeah. This function is monotonic increasing over its domain. Monotonic increasing. Cool. All right, so there's a new parent function, e to the x. Remember, e is not just a vowel anymore now, it is the natural base. And in geometry, you use pi a lot. In Precal and calculus, we're going to use e almost as much as y'all use pi in geometry.
Would the function eventually become vertical almost?
It's going to get so steep that it looks like it's vertical, but it never becomes truly vertical because it does continue to go out to the right forever and ever. The domain is all real numbers. Okay, but you're going to get to a point way out on the x-axis to the right that it looks like it's going straight up, even though it's not. It's still going out to the right. All right, this one here, how would you read that? Yeah, the L is for log, but it's a very special log. You've probably had experience with this, log of x, like that. Right? Now, if you have log of x and there is nothing written between the g and the x, you remember there was a base that you assumed? It's 10, right? So this would be what we call a common log, or the scientific log. All right, and your calculator is programmed to handle a log base 10. We're going to study logs later on again, so you'll have a better understanding of what this is. So if you see log with nothing written there as a subscript after the g, it's assumed to be base 10, which is the common log, the scientific log. If you see like a base 7, that's log base 7. Well, what we're going to be talking about is ln of x, which is the same as log base e. Okay? So the way we read that, I'm just going to erase that right there. We read this as the natural log. ln, logarithmic naturalis, the natural log. And it's really log base e. Now what you're going to learn, if you don't remember this already, logs and exponential functions are related to each other. Do you know how they're related?
They're the opposites.
Not the opposites.
Inverse.
Inverses, yes. One of them undoes the work of the other. If you exponentiate a number, you're like, oops, I didn't mean to do that. You could take the log of your result and get back to your original value. Just like if you take the square root of a positive number, it undoes squaring it. So x squared and the square root of x for positive x are inverses of each other. They undo each other's work. Same thing with logs and exponentials. As long as the base is the same, they're inverses. So the inverse function of e to the x is log base e to the x, or what do we call it? The natural log of x. And when I write it, I use cursive usually, for no particular reason other than it just flows nicer. ln of x. Now let's talk about what the ln of x is. If it's truly the inverse of e to the x, then its inputs and outputs should be switched. So on the graph of e to the x, or on the function e to the x, when you plug in a 0, you get out a 1. Okay? So imagine there's a machine, and you plug in a 0, and you get out a 1, and you're like, oops, I need my 0 back. I want a machine that when I plug in a 1, I get back my 0. Guess what the machine is? ln of x. So guess where the x-intercept is? 1, 0. Because e to the x has a y-intercept at 0, 1, its inverse function, the natural log of x, has an x-intercept at 1, 0. Because e to the x has a horizontal asymptote at y equals 0, the natural log function has a vertical asymptote at x equals 0. Yeah. There's a VA at x equals 0. What's the domain of this function? 0 to infinity, not including 0. Hey, that was the what of e to the x, 0 to infinity? The range. That makes sense. If the range of e to the x is 0 to infinity, that should be the domain of its inverse. What was the domain of e to the x? All real numbers. Guess what the range of its inverse is? All real numbers. And the natural log graph takes on all the y values. Any symmetry here? No. Is it monotonic? Yeah, it's also monotonic. Yeah, monotonic increasing. Let's look at the end behaviors. Yeah, you're talking about how to get the graph of an inverse from the function. You would reflect, the way you get the graph of an inverse from an original graph is to reflect it across a line, and I think you're trying to think about it, how it works. You reflect it across the line. Does anyone remember? We'll study that later. You reflect it across the line y equals x. If you reflect the function across this, y equals x, you're going to get the inverse. So just very quickly here, if you reflect that across the line y equals x, it's going to look something like this. Yeah, and the way you do it algebraically is you interchange x and y and resolve for y. So notice that the red line and the blue line, or the purple line there, if you folded it along the line y equals x, they would coincide with each other. And the red line, of course, would be some type of what type of function? Exponential, and the purple one would be some type of log function. So we're going to study that again when we study logs and exponentials. Right now, I just want you to memorize this function, the natural log of x. What is the natural log of 0? If I said f of 0, f of 0 would be the natural log of 0, which is, well, what do we have there? Vertical asymptote. Is there any point or dot on the y-axis? No, so it doesn't exist. You can only take the log, as we said right there, of positive numbers. Okay? You can only take the log of positive numbers. What would be the limit as x goes to infinity of this function? What's the right end behavior? Infinity. Now this is an interesting infinity because this graph almost looks like it's tapering off, approaching some horizontal asymptote, but it's not. It goes up forever and ever and ever, but increasingly slowly. It's one of the slowest growing functions out there. Does it have any left end behavior? What would be the limit as x goes to negative infinity of this function? When I say negative infinity, left end behavior, I'm not talking about the leftmost part of the graph. I'm talking about way out to the left over here. It does not exist because the graph doesn't live out there, right? Now, here's a question that we could talk about. What is the limit as x approaches 0 from the right-hand side? Negative infinity. Good, right? As we hop on the graph of the natural log of x and we start heading towards 0 from the right side, that's the only side from which we can, we're going down, 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 right? Forever. So that's negative infinity. And if we recall the definition of a vertical asymptote, if I just told you that, you'd be like, oh, the graph must have a what at x equals 0? Vertical asymptote. That's what's forcing the y values to decrease without bound as we approach 0 from the right. Okay, anyone want to say anything else about the natural log of x before we move on? Who came up with logs? We'll study logs in greater detail later on, and we'll have a conversation about a Scottish mathematician named John Napier. Okay, and he's the guy who kind of introduced the notation of logs. Okay, but he didn't call them logs; he called them bones. He called them Napier's bones, which kind of sounds a little spooky, right? Yeah. All right. 1 over x, we've seen this guy before. 1 over x, that's the old what function? Reciprocal. You know why we call it the reciprocal function? You know what it does to its input? Reciprocates it, right? F of 5 is 1 over 5. F of 7, 1 over 7. What's F of 1/8? 8. All it does, it's a machine that takes the input and flips it. That's pretty cool. So here's what it looks like. We've seen it before. It's really a rotated hyperbola. It has a horizontal asymptote on the x-axis, and it also has a vertical asymptote on the y-axis. A hyperbola would be one of these. This is just rotated. You need to study conics in Algebra 2. You had circles, ellipses, hyperbolas, parabolas. That's okay. You don't need to know it's a hyperbola. It just looks like that. It comes from the vertical asymptote, departs, and approaches the horizontal. It is a hyperbola. It's a rotated hyperbola. If you rotate it 45 degrees, the x and y axis become the slant asymptotes. Yeah. It's okay. You don't need to know that. Just know that this one looks like that. The reciprocal of a positive number is a positive number, and the reciprocal of a negative number is a negative number. Now notice if you start right here, that's a very small positive x value. What's the reciprocal of a very small positive number? No, like 1/10. What's the reciprocal of 1/10? 10, a big positive number, right? And if you go out further, like way out here, that could be like 1/10. I'm sorry, we're out here at x equals 10. What's the reciprocal of 10? 1/10, yeah. So that's why it comes from infinity and goes to 0. The reciprocal of a small number is a big number, and the reciprocal of a big number is a small number. So this one lives in quadrants 1 and what? 3. Good, 1 and 3. What's the domain? All real numbers except the ones that don't work, which is 0. Yeah. So it's the set of all x such that x ain't 0. What's the range? We get the range from the graph. Right. The set of all y such that y is not 0. Is this function monotonic over its domain? It's not decreasing as you come in from the left. Is the graph going downhill? Yeah, it is. And when you get on the other side of the vertical asymptote, is it going downhill? Yeah. So this function is monotonic, decreasing over its domain. It is. And there's some kind of magic trick going on at 0, right? You like go through a wormhole. You exit the bottom and come out the top. Kind of like the old Pac-Man game when you exit screen left and come in screen right. That was cool. Screen right. Yeah, Pac-Man. Okay. And then the last one here is the V for victory graph, the absolute value of x function. Have you all seen this one before? Yeah. This one is basically the line y equals x everywhere to the right of 0 and including 0. So what's the slope of that line? What's the slope of a line when it's, 1 over 1. So the slope is 1, up 1 over 1, up 1 over 1. What would be the slope everywhere to the left of 0? Negative 1, right? And it comes in and there's a sharp turn right there. There's a sharp turn. We can call that the vertex, but we can also call it a what kind of min? We can call it an absolute min. Good. Is it also a local min? Yeah, it's also a local min. Absolutely. Okay, so that one you'll have a little bit of familiarity with. We're going to be adding to this list as the year goes on, including some sine and cosine graphs later on. But right now, these 8 functions you need to know very, very well, so that if you see an equation that is some offspring of these, you can identify the parent function, kind of visualize what that looks like, put your equation into a standard transformation form that's going to allow you to do the same kind of analysis each and every time, manipulate these graphs, and get the final result very quickly, all without a what? Calculator. Who needs a calculator when you got one right here, right? Example 1. Sketch the following piecewise function. I don't even know if a calculator would help me for this anyway. Do y'all know how to sketch piecewise functions on the calculator? You do? There is a way, but I'm not even going to show you. Because again, do we need a calculator? No, because we have one where? Right there. Right there. If you thump and there's a hollow sound, that's not good. Okay. What's that? Correct. In the old sense of the term. Right. Yeah, calculators used to be like people, like there goes a calculator. Right? Because that's what you call people. Right. Now if you say there goes a calculator, you're looking for a TI-84 with legs, right? And sometimes they do grow legs and walk out of here, so that's why we have this basket, right? Make sure you put your ID. All right, example 1. Check for the domain, range, symmetry, continuity, relative extrema, blah, blah, blah. Okay. You look at that problem, and it's g of x equals, that's the name of the function g, the independent variable is x. How many pieces? 4, right? So kind of appropriate around Halloween to be looking at a Frankenstein's monster of a problem. Some guy made this in his laboratory. It's part x, it's part x squared, it's part square root of x, and it's part x to the negative first. What's x to the negative first, also known as? That's your reciprocal function in disguise, right? Okay, so do we know how the individual pieces look like? Hopefully, right? We just went over them, so you visualize them maybe in your head. How are we going to put them all together? They may or may not connect. What we're going to do, though, is draw the piece of the graph on the interval for which it's being defined. So we need to have ourselves a place to graph it. So there's my x and y axis. Start by looking at the x values where it changes from one to the other. So the first x value is 0. No, -1. Very good. I'm going to go ahead and draw a -1 right there. I don't want to draw it too close to the y-axis because I want to make my graph kind of stretched out a little bit. Now, do we know what the graph of x looks like? Sure. But do I want to draw it like that? No, because I'm only drawing it where? To the left of -1 and at -1. So if I could just get rid of the piece that doesn't live to the right, or maybe I just draw it coming in with the slope of 1, kind of aiming toward the origin. You notice that the line y equals x would go through the origin. So if you kind of use the origin as another target without drawing it, there you go. Now, boy, oh boy, wouldn't it be nice if we knew the y value right there where the line stopped? That would be the limit as x approaches -1, right? How do we find that out? Sure, we could just plug in a -1 right there. What do you get when you plug in a -1 for x? -1. Right, so okay. We just answered this question too. What would be the limit as x approaches -1 from the left-hand side of g of x? -1. Do you think on a test, if this were a multiple choice question and I just gave you that piecewise equation and I asked you that question, you can get -1 without graphing it? Yes. I hope so. Because you'd be like, oh, left of -1, that's less than -1. I'm going to plug that in there and get a -1. Okay, good. Next piece, between -1 and 0. So that's going to be in this little span right there. It's going to be our old friend x squared. Boy, wouldn't it be nice to know the y value where x squared starts at -1. How'd you get that? Plug it back in, right? If you plugged in and you got a 1, is it going to be graphed with a solid dot or an open circle? An open circle. So I'm going to come up here and call that 1, and at the point -1, 1, I put an open circle. Now that would end up being the limit from the what side of -1? That would be the limit as x approaches -1 from the right-hand side. It's +1. Now, it would also be nice to know where x squared ends up at 0. We kind of know that, though, right? That's its vertex. But again, you could plug in your 0. What's 0 squared? 0. And I'm going to put a solid dot or an open circle. Open circle. Now, all I have to do is connect those two open circles with what I know the graph of x squared to look like, which is a wiggly line, right? Yeah? Yeah? Huh? No. How about one of these? Huh? That looks like a parabola. No. Okay. It looks something like that, right? It would normally bounce at the origin and go up. There you go. What would be the limit then as x approaches 0 from the left? 0, right? Remember, the limit doesn't care if the dot is filled in or open, does it? That's the function value's concern, not the limit's concern. All right, so far so good. Now we're picking up at 0 and we're going to go to 1. So 1's going to be out here. And it's going to be our old friend. These are all our old friends, right? Radical x. We know what radical x looks like? Mm-hmm. We know that he starts at the origin, doesn't he? Radical x doesn't start at the origin? Yeah, he does. Yeah, now, do I fill it in or leave it open? It says equal to, right? So I get to plug it in. Oh, boy, boy, boy. So I'm going to use a different flavor here. But that open circle that the parabola did not claim is now claimed by the radical function. Well, I also want to know the y value where it ends up. So if I plug in a 1, I get the square root of 1, which is what? 1. And am I going to put a solid dot or an open circle? Open circle at the point 1, 1. All right. Now I'm going to connect those solid dots and open circles with what the radical function looks like, which is something like this. You can kind of exaggerate it a little bit, right? Now notice I know the answer to 2 more limit questions. What would be the limit as x goes to 0 from the right-hand side? 0. And you could have found that out without graphing it because right of 0 is greater than 0, and by direct substitution, plugging in a 0 here, you get 0. What would be the limit as x goes to 1 from the left-hand side? 1. And again, greater than, from the left side of 1 is less than 1. Plug a 1 into the square root of x and you get 1. So you can find those limits at the x values where it changes without graphing it. And then finally, to the right of 1, it's x to the negative first, which we also recognize as 1 over x. Boy, it'd be nice to know the y value where he picks up, right? So what would be the limit from the right of 1? 1. Do I put a solid dot or an open circle? Open circle because it's strictly greater than. So at the point 1, 1, I put another open circle. Okay, so they're sharing that open circle. Sharing is caring. And then what does the graph look like to the right of 1 if it's 1 over x? It would normally come from the vertical asymptote, yes? And it would come down and it would pass to the point 1, 1, and then continue off to the right, approaching what? 0. So do we have a horizontal asymptote? Yes. So we're looking at that piece of the graph so you can kind of, again, exaggerate the curve. There you go. And now we know the answer to this. What would be the limit as x approaches 1 from the right? Well, right of 1 is greater than 1. You could plug it in and get 1. What would be the, yeah, go ahead.
The reason that we don't worry about the other part of the reciprocal function is because it's only talking about...
Right. The way it's defined, it says only look at the reciprocal function to the right of 1. Don't look to the left of 1. So the vertical asymptote that we know exists for 1 over x, it's out of play, isn't it? Yeah. We're only looking at that one little piece. What would be the limit as x goes to infinity? 0. Now you can look at your graph and determine that, but without the graph, you could say infinity, infinity. Hey, I think infinity is greater than 1, so you can use that piece. And what happens to 1 over x as x goes to infinity? 1 over 10, 1 over 100, 1 over a million, 1 over a gazillion. Approaches 0, right? Good. What would be the limit as x goes to negative infinity? What's the left-hand behavior? Yeah, this is going down, down, down to negative infinity. You could have determined that also without the graph, right? Because negative infinity, I do believe, is to the left of negative 1. And what happens to the graph of x as x goes to negative infinity? Plug in a huge negative number for x, and you get a huge negative number. All right. Don't that pretty, as they say down in Cajun land. Don't that pretty.
So there's a horizontal asymptote everywhere. Right?
There is a horizontal asymptote at y equals 0. But it only affects the graph on which end of the graph, Anthony? The right end of the graph. Yeah. Does this graph pass the vertical line test? Sure does. So it is a function. Let's go ahead and talk about the domain. What's the domain of G?
Wait, if you have, say that dot above a solid dot was solid as well, would that not have to break the line class?
If this dot up here was solid, then it would not be a function, right? It would not be a function. It would still be a relation, but it wouldn't be a function. Very good. And notice that this dot right here at the origin got filled in, but it only got filled in by one of them. So it's very important when you're defining the function here, someone that you meet on the street might argue that you don't lose any information in this problem if you say that it's going to be x squared to the left of 0 and 0, and if you let it be the square root of x to the right of 0 and 0, simply because they have the same y value at 0. Don't let that person influence you, because you know what? They may be right in saying that the function's continuous at the point, but this is a violation of a function by definition, because what have you done? You have now assigned, when x is 0, you have assigned it to what? Two different functions. Who cares if it's the same y value? It violates the spirit and the definition of a function. So even though they do share that y value, only one of them gets to claim it. So if you want the x squared to claim it, you can go ahead and put less than or equal to 0, but then you would do what with this other one? Yeah, you would just say, okay, there you go. And the graph doesn't look any different. Only one can claim it to be a function. Okay, what was the domain? Did we talk about it? Yeah, it's the set of all x such that x cannot equal 1. Could you get that without the graph? I would hope so, yes. Here's how you would do it. You would look at your individual pieces first, and you'd say, okay, this, if by itself, would have a domain of all real numbers. This by itself has a domain of all real numbers. This one only exists to the right of 0 and at 0, and that's exactly where we're defining it, so it's good. This one here is x can't be 0, right? Because we get a vertical asymptote. But we're not even looking at it at 0, so it should work. So all the pieces by themselves don't have any discontinuities over the intervals for which they're being defined. So once you do that, then you come over here and see where is it explicitly defined. It's defined to the left of -1. It's defined at -1. It's defined to the right of -1. It's defined everywhere to the left of 0. It's defined to the right of 0. And it's defined at 0. And it's defined to the left of 1. And it's defined everywhere to the right of 1. Uh-oh. Guess where it is explicitly not defined? At 1. And so that's another way to get the domain. Now the range is a little bit harder to get unless you have the graph. So to get the range, let's just look at the y values on the graph. What y values does this graph take on? You want to do interval notation? I like that. So coming in from the bottom, -infinity up to -1, right? Do we actually get to y equals -1? We do. There's a solid dot. So what goes around -1? A beefy bracket or a wimpy parenthesis? Beefy bracket. Union, what's the next y value that we pick up at? 0. I spy a y equals 0 right here. We have a dot at the origin, so that would be 0 with a bracket. And then we get all the y values from 0 up to what? 1. Do we get 1? No, we had 2 shots at it and neither one worked. Bummer. So a parenthesis. Do we have any values above 1? No. So there you go. That's an interesting range. We can tell what type of discontinuities we have, right? At x equals -1, there's a... No, we call that a jump. And again, the jump is going to exist simply because the limit from the left is -1 and the limit from the right is +1. It doesn't matter what the function value is for a jump. As long as the two limits are different finite y values, there's a jump. Is there a discontinuity at 0? No, because based on a 3-step definition, the limit from the left of 0 is 0, the limit from the right of 0 is 0, and the function value is at 0 is 0. So They all three equal each other. What type of discontinuity do we have at 1? That's a whole. And that's going to exist anytime the limit from the left and right are the same, and therefore the general limit exists, but the function value either doesn't exist or it's something else. Okay, so that was a nice little application of your parent functions. What else did we forget to talk about? Oh, any symmetry to this graph? No y-axis, no origin. No. How about any local extrema? Do we have any local mins?
At 0.
Yeah, at x equals 0, we have a local min of 0. Yeah. So we have a local min of y equals 0 at x equals 0. If you zoom in this local vicinity, that y value is the lowest one. Are there any other local mins? Is -1, y equals -1, is that a local minimum value?
No.
No. If you look immediately to the right, you have values that are higher, so that's good. But if you look immediately to the left, you have values that are lower. So it's a relative nothing. That's all I see as well. Do we have any local maxes? We do have a local max? A local max of 1? Well, do we even have a y value of 1? To be a local max, the y value has to exist. Yeah, there is no local max of 1, but what would be the first number less than 1? 0.999999999999999. There is no first number less than 1. So do we have a local max at x equals 1? No. Do we have a local max over here? No. Now, if either one of those open circles were filled in, that would be a local max value, right? Including this one over here. That would still be a local max if it were filled in, because immediately to the right, we have values that are lower, and immediately to the left, we have values that are lower. But because they're not filled in, neither one of them is. Is this a local max right here? Now, this one's kind of tricky because you notice, like, if you look in this vicinity, right, there we are looking in the vicinity, he appears to be the highest value, right? But when we look in the vicinity, we're looking at x values. And notice that if you look immediately to the right, boom, you have y values that are much greater. So he's not a local max. So there's no local maxes, none. La 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 la. Any other comments on this handsome beast? It's not really a beast, though, is it? Yes, Kevin.
Would the dot at -1, -1 be a local max and built-in portion without -1, 1?
Yes, great question. If this had been an open circle here, and this had been filled in, now we would have a local max of y equals 1 at x equals -1. And again, here's the ultimate test. If you look immediately to the right, values are lower. If you look immediately to the left, values are lower. That's the ultimate criteria. When I say immediately to the right and immediately to the left, that gives it that local feel, that relatively small interval. So notice then, by that criteria, a local max or local min can't occur at an endpoint. It can't live on a cul-de-sac. It has to live on a through street, because you have to be able to look left and right and find values that are lower on either side to be a local max, or values that are higher on either side to be a local min. But of course, it has to first be a y value. It has to exist. So because it was actually open, there was no local max. Good question. Any other questions? Could we say that 0 is a local min since it's approaching 0 as we go out to the right? No, because remember, this function is actually still doing what as we go out to the right? Increasing or decreasing? It's decreasing. And we're going to run out of the ability to appreciate that, because it's going to start looking to us like a horizontal line. But if you zoom in far enough down the line, you'll actually see it going downhill. So any point along that line, to the left you have points that are higher, and to the right you have points that are lower. So it's never going to have a local min. It's decreasing forever. It's getting closer and closer to 0. All right, standard transformation form. This is what I call standard transformation form. You might have just called it the transformation form in Algebra 2. It's the same thing as vertex form for a parabola, but in general I call it standard transformation form. So if we start with some parent function or mother function f of x. We can change things in the equation, and if we can identify them in a standard form, it'll affect every single graph in the exact same way. Every single time, regardless of what the original graph looks like. And so you have enough experience with this. The new function, the transform function, we're going to call g of x, and we're going to write it as a times f of b times x minus c, close, plus d. And this right here tells you the summary of everything that a and b and c and d collectively do. And I'm going to let you read that for homework. What I'm going to do now is briefly talk about it. There are two different ideas in standard transformation form that you need to understand. One of them is inside versus outside, and one of them is multiply, divide versus add and subtract. If you can memorize those two different ideas and then put them together in combinations, you'll have it. Let's look at the inside-outside first. This is inside. Maybe I should use a red highlighter. Inside the function is what takes place inside the f of. Okay? Anything that takes place on the inside of a function is going to affect the graph horizontally because they're affecting the x values. Now, what does it mean to be inside a function? Let's go look up here at our parent functions. To be inside the x function, because it's really x to the first, means to be right here. What does it mean to be inside the x squared function? Well, it means that you're going to be affecting the x before you square it, before you apply the function. What does it mean to be inside the x cubed function? Well, again, you're affecting the x before you cube it. What does it mean to be inside the radical function? This is a little bit easier. It means to be in the radical before you apply the function, which is square root. What does it mean to be in the exponential function? It means to be in the exponent itself. What does it mean to be in the log function? It means to be in this. We call this, I might as well give this to you now, we call this the argument. The argument is the thing you're taking the log of. And what does it mean to be in the reciprocal function? Well, it means to be in the denominator with the x. And of course, what does it mean to be in the absolute value of x function? It means to be in the absolute value bars. So every function has its own inside before you apply the actual function and an outside. If it's affecting the graph on the inside, it's affecting the graph horizontally. The other dynamic that you need to understand is the outside of the function. A and D are affecting the graph on the outside. And if it's on the outside, it's going to be affecting the graph vertically because it's affecting the function values, which remember are also the y values. Now, what does it mean to be outside every single particular function? Well, again, in the square root or the x to the first, it means to take place outside. So we have really a 1 plus 0. Outside here, we have a 1 plus 0. Outside the x cubed, again, it's after we cube it. For this one, it's going to be outside the radical, after you apply the radical. For e to the x, it's going to be anything that's outside the exponent. So once you know where the inside is, the outside is everything else, after you apply the actual function. This will be 1 times 1 over x plus 0 again. This will be 1 times the absolute value plus 0. So if it's outside, it affects the graph vertically. If it's inside, it affects the graph horizontally. That's a hugely important concept. Tomorrow, we'll look at very briefly the other dynamic, which is multiplication and division versus addition and subtraction. So I guess it looks like they're going head to head. You can place your bets. Who's going to win? We all win, okay? Multiplication and division is going to affect the graph a certain way. That's going to be your stretches, your dilations, your compressions. And addition and subtraction is just going to be moving it around. Those are your shift or translations. Yes?
We have 1 times MC, 1 half x minus 2.
Then the 1/2 x is on the inside, because it's then that's going to affect the graph horizontally. That's actually going to be a horizontal stretch by a factor of 2. Mm-hmm. If it's on the inside, yes. It's not half as wide, it's twice as wide. Everything on the inside, as you're going to see, is the opposite of what it appears. So just like if it were x minus 3, it doesn't move it to the left 3, does it?
Wouldn't one have to get more narrow because
No, not if it's on the inside. No. If it's on the inside, we'll look at it tomorrow. Because when you're talking about just plain old x, inside and outside, there's really no difference. If it's a 1/2 on the outside, it's going to compress it vertically by a factor of 2, which kind of makes it a little bit wider. If it's on the inside, it's going to stretch it by a factor of 2, which also makes it wider, less steep. So they're equivalent. Y'all have a fantastic day.